Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Okay, let's unpack this. There's this question, it's probably as old as thinking about planets, really. What was Earth actually made of? I mean, before it became the Earth we know. What were the starting chemicals? Yeah, what was the recipe for proto-Earth? And for decades, I think it's fair to say, the scientific line has been pretty clear, almost absolute.
Absolutely. The standard story was that whatever Earth started as, chemically speaking, got completely wiped out. Obliterated.
Right, by the formation of the moon, the constant geological churning.
Yeah.
Basically, the chemical slate was wiped clean. That's what I learned anyway.
That was the textbook answer. The idea was that the heat and violence involved just homogenized everything, mixed it all up into one sort of standard Earth composition.
But now, now we're diving into something pretty groundbreaking. There's a major paper just out in Nature Geosciences that seems to turn that whole idea on its head.
It really does.
Yeah.
It's a significant challenge to that long-held view.
The claim, and it sounds almost like science fiction, is that scientists have found actual physical remnants of that original proto-Earth, material from 4.5 billion years ago, before the big impact.
Preserved chemical fingerprints, exactly. Material that somehow survived the event that was supposed to reset everything.
So our mission today, for you listening, is to figure out how. How can a tiny chemical signal, an imbalance in some old rocks, actually rewrite our planet's entire origin story? It feels like a shortcut to understanding the very first ingredients of our solar system.
And it is a shortcut, in a way, because, as you said, the giant impact theory was so central. The collision, thought to have formed the moon, was considered so devastating that it effectively erased any chemical memory of what came before.
You couldn't look at Earth rocks and know what proto-Earth was like.
Precisely. The assumption was ironclad.
Yeah.
The original stuff was gone, melted, mixed in. If you wanted to know about Earth's building blocks, you had to look outwards, at meteorites, things formed elsewhere that didn't go through that cataclysm. But this new work, and it's a strong team, researchers from MIT, Carnegie, ETH, Zurich, Scripps, they're saying, hang on.
Maybe some of it is still here.
Exactly. Maybe some of those original chemical ingredients are preserved right here, deep within the Earth. We might not need to look only to space. We might need to look deeper under our feet.
Which takes us right back to that conventional story, the one that's now being challenged. Let's quickly recap that. The early life of a planet.
Okay, so picture the very beginning. The solar system isn't planets yet. It's just this huge swirling disk of gas and dust around the brand new sun. The solar nebula.
Like a cosmic soup.
A very hot, very chaotic soup. And gravity starts doing its thing. Dust grains stick together, become pebbles, pebbles clump into rocks.
Accretion, right?
Accretion, yes. Building up layer by layer. These clumps form the first meteorites, the building blocks, and they keep colliding, merging, getting bigger and bigger.
Until you get planetesimals and eventually proto-Earth and its neighbors.
Right. And this proto-Earth, in its earliest stage, wasn't like Earth today. It was likely rocky, yes, but incredibly hot. Constantly bombarded by more material, probably covered in bubbling lava, a global magma ocean.
Sounds pretty inhospitable.
Definitely not a place for life as we know it.
Yeah.
It was still accumulating mass, still forming, chemically different from the planet we live on.
And then the event, the catastrophe. And this happened fast, geologically speaking.
Extremely fast. We're talking less than 100 million years after the planet first started forming, so very early in its life.
And this wasn't just another collision. This was the collision, the giant impact.
The one that's thought to have created our moon. The leading theory, the giant impact hypothesis, posits that a massive object, something roughly the size of Mars,
Often called Theia.
Theia, yes, slammed into this young molten proto-Earth.
The energy involved must have been, well, unimaginable.
Truly astronomical. Hitting an already superheated molten planet with something that big, it would have vaporized huge amounts of rock, the mantle, the crest, threw enormous plumes of debris into orbit.
Which eventually clumped together to form the moon.
That's the prevailing model.
Yeah.
But the key consequence for our story today, the reason this new finding is so radical, is what that impact supposedly did to Earth itself.
It scrambled everything.
Completely. The conventional view, the one taught for decades, is that the impact energy and the subsequent remelting led to total planetary homogenization. The planet's interior got mixed, like a cake batter.
Resetting the chemistry.
Exactly. Any original chemical signature from proto-Earth was thought to be utterly obliterated, mixed inseparably with the material from the impactor. Thea, gone forever.
Which, again, makes total sense when you think about the sheer violence. So naturally, scientists concluded, look to meteorites. They're the only pristine witnesses left.
It was the logical conclusion. If everything here got scrambled or reset, the only way to guess the original ingredients was to analyze things that weren't here during the impact. Untouched samples from the early solar system.
So the assumption was you pick up any rock on Earth, from the crust, the mantle, wherever. It should basically have the same post-impact chemical fingerprint.
Correct. A homogenized signature. Finding something different, something that harks back to the pre-impact era, suggests a part of the planet somehow escaped that total mixing. It implies some deep reservoir remained isolated.
Which sounds almost impossible.
It sounds incredibly unlikely given the scale of the impact. That's why this new result is so startling. Nicole Nee, one of the lead authors on the paper, really captured this. She said, this is amazing because we would expect this very early signature to be slowly erased through Earth's evolution.
Even if it survived the impact, you'd think billions of years of geology would smooth it out.
You'd think so. Convection in the mantle, melting, plate tectonics, all these processes tend to mix things up over geological time. The fact that they found any remnant implies we need to seriously reconsider how effective the giant impact was as a chemical eraser.
And maybe parts of our planet are chemically distinct, zoned, and have been that way for 4.5 billion years.
That's the profound implication here. Maybe Earth isn't as well mixed as we assumed.
Okay, so if the impact didn't completely erase everything, how did they find the leftover bits? What's the chemical code, the tracer they used to unlock this? You mentioned isotopes.
Right. It all comes down to isotopes, and specifically isotopes of potassium.
Let's break that down. Isotopes. Okay, I remember this from chemistry. They're like different versions of the same element.
Exactly. Same element means the same number of protons in the nucleus. That defines what the element is. So potassium, symbol K, always has 19 protons.
Isotopes have different numbers of neutrons.
Correct. Same protons, different neutrons. This changes the mass slightly, but not the chemical behavior mostly.
Okay.
And this slight mass difference is absolutely critical when you're dealing with really high energy events like planets forming or smashing into each other.
Okay. So potassium, what are its isotopes?
Potassium has three main naturally occurring ones. Potassium-39, K39, potassium-40, K40, and potassium-41, K41.
Got it. 39, 40, 41.
Now, on what we consider standard modern Earth, the stuff that makes up the bulk of the crust and mantle, K39 and K41, are overwhelmingly dominant. They make up almost all the potassium.
And K40.
K40 is there, but it's a tiny, tiny fraction, a vanishingly small percentage compared to the other two.
Okay, so that specific ratio, that balance loads of 39 and 41, hardly any 40. That's the chemical signature of normal post-impact Earth.
That's the homogenized signature, yes. But why potassium? Why is it the key?
Good question. Why not iron or silicon or something more common?
It comes down to volatility. Potassium is what's called a moderately volatile element.
Meaning it evaporates relatively easily when heated.
Exactly. Think about the giant impact again. Immense heat, vaporized rock.
Yeah.
Volatile elements like potassium should have been strongly affected. They might have been lost to space, or fractionated, meaning the different isotopes might have behaved slightly differently in that extreme heat.
Okay, so its volatility makes it sensitive to these huge events.
Very sensitive. If the impact truly mixed everything perfectly, then the potassium isotope ratio should be the same everywhere, reflecting that final homogenization event. But if some material didn't go through that intense heating and mixing,
it might have preserved a different potassium isotope ratio from before the impact?
That's the hypothesis. And this team, led by Nee, actually laid the groundwork for this in a previous study back in 2023. They weren't looking at Earth rocks then, they were looking outwards.
At meteorites?
Yes. They analyzed a whole range of major meteorite types, carbonaceous chondrites and statite chondrites, ordinary chondrites. These are like snapshots of the different chemical reservoirs that existed in the early solar system, the potential building blocks of planets.
And what did they find in those meteorites?
They found that the potassium isotope ratios were different from standard Earth and different from each other.
So not the standard Earth mix of K39, 40, and 41.
Exactly. Some meteorite groups had slightly more K41 relative to K39, others slightly less. They showed distinct potassium isotopic anomalies.
An anomaly meaning just different from the Earth standard.
Different from the bulk Earth standard, yes. And this wasn't just random noise. It varied systematically
Yes.
between different classes of meteorites.
Okay, this is clicking now. The different meteorite types represent different early solar system ingredients, and they have unique potassium isotope barcodes.
You got it. That was the breakthrough concept. This isotopic anomaly, the specific balance of K39, K40, and K41, tells you something about the conditions, the temperature, the pressure under which that material formed. It acts as a tracer.
A tracer for Earth's original building blocks.
Precisely. Nii and her colleagues realized that if they could find material on Earth that showed one of these non-standard potassium isotope ratios, especially one that matched some meteorite group, it would be strong evidence that this material predates the final homogenization. It survived.
So the 2023 study established potassium isotopes as the tool, the chemical barcode.
Yes. It gave them the crucial tool. What's fascinating is how it shifted the search. Instead of just looking at space rocks to guess Earth's original makeup,
They started looking for the signature of those space rocks, or something like them hidden within Earth itself.
exactly. Find the barcode on Earth and you've potentially found a piece of proto-Earth.
Right. Okay, so you have the tool, the potassium isotope anomaly. You suspect some proto-Earth material survived. Where on Earth do you even begin to look for something like that? Something 4.5 billion years old that somehow dodged a planetary-scale cataclysm.
That's the next critical piece. You need a strategy. You can't just drill anywhere. The logic has to be find the most isolated, the oldest or the deepest materials accessible, places that might have been shielded.
Shielded from the impacts mixing and shielded from billions of years of geological reprocessing. Makes sense. So where did they target?
They focused on two main categories of samples, hitting both deep time and deep Earth.
Okay, deep time first. What does that mean?
That means looking at the oldest preserved rocks on the Earth's surface. They collected samples from ancient crustal areas in Greenland and Canada.
Why there specifically?
Those regions contain cratons. Cratons are the incredibly old, stable cores of continents. Some of these rocks are billions of years old, among the most ancient materials we have access to on the crust. They've largely avoided being recycled back into the mantle through processes like subduction.
So potentially little pockets of very old crusts that might remember an earlier time.
That was the hope for the deep time samples. Then, for deep Earth, they looked at lava.
Lava. But isn't lava relatively new rock?
The lava itself cools into new rock, yes. But where the lava comes from is key. They specifically analyzed samples from Hawaii.
Okay, Hawaii, famous for volcanoes. Why Hawaiian lava?
Because Hawaiian volcanism is different from, say, volcanism at tectonic plate boundaries. Hawaii sits on a hotspot. It's fed by a deep mantle plume.
A plume, like a conveyor belt of hot rock rising from deep inside the Earth.
Exactly. These plumes are thought to originate from way down, perhaps even from the boundary between the core and the mantle, a region called the D's layer, D double prime. It's about as deep as you can sample material from.
Wow. So the idea is, if any proto-Earth material got trapped deep inside the planet, protected from the mixing, a mantle plume, like the one feeding Hawaii, might bring tiny samples of it up to the surface.
That's the hypothesis. These plumes could be tapping into a deep, ancient, potentially unmixed reservoir. So you have the ancient surface rocks from cratons and deep mantle material brought up by plumes, two prime candidates.
Okay, they've got their target samples, Greenland, Canada, Hawaii. What happens next? This isn't like a simple chemistry test, I imagine. Measuring tiny isotope differences sounds incredibly difficult.
It's extraordinarily difficult. The analytical process here is painstaking, requiring extreme precision and cleanliness.
Walk us through it. What do they do with these rocks?
First, the rock samples had to be crushed into a very fine powder. Think like talcum powder consistency.
Okay, pulverized.
Then this powder is dissolved, usually using very strong acids like hydrofluoric acid to break down all the silicate minerals. Everything has to go into solution.
So you end up with a liquid containing all the elements from the rock.
Correct. And then comes the really tricky part. Isolating the potassium. You need to separate the potassium atoms from everything else in that complex chemical soup. The iron, the silicon, the magnesium, calcium, trace elements, everything.
How do they even do that?
Typically using a technique called ion exchange chromatography. It involves passing the solution through special columns packed with resins that selectively grab onto certain elements. It's a multi-step process, carefully washing away the unwanted elements until, ideally, you're left with just the potassium.
And it has to be incredibly pure, right? Contamination would ruin the measurement.
Absolutely critical. We're looking for minuscule variations in isotope ratios. Even a tiny bit of potassium contamination from the lab environment, dust, glassware, reagents, could completely skew the results. This requires working in ultra-clean laboratory conditions.
Okay, so they've powdered, dissolved, and painstakingly isolated pure potassium from these ancient or deep samples. Now what? How do you measure the isotopes?
That requires a very specialized instrument called a mass spectrometer. Specifically, often a thermal ionization mass spectrometer, TMS, or a multi-collector inductively coupled plasma mass spectrometer, MCICP-MS.
Sounds complex.
It is. Basically, you load the purified potassium sample into the machine. It gets ionized, turned into charged atoms. Then these ions are accelerated through a magnetic field.
And because the isotopes have slightly different masses,
They get deflected differently by the magnetic field. Heavier isotopes like K41 bend less, lighter ones like K39 bend more. The instrument has detectors precisely positioned to count the ions of each mass arriving.
so it can measure the exact ratio of K39 to K40 to K41 with incredible precision.
Extraordinary precision, down to parts per million or even better. That's the level you need to detect the subtle anomalies they were looking for.
And the results, after all that work on the Greenland, Canada, and Hawaii samples.
The results were, well, remarkable. Consistent across these specific samples. They found a potassium isotopic signature that was clearly measurably different from the standard homogenized bulk Earth signature found in most other rocks.
Different how? What was the anomaly?
Specifically, they found a deficit in the potassium-40 isotope.
A deficit, so even less K40 than the already tiny amount we expect in normal Earth rocks.
Exactly. Remember, K40 is already the runt of the litter, isotope-wise. A very small percentage. These samples from the cratons and the Hawaiian plume source had an even smaller fraction of K40 relative to K39 and K41 than the standard Earth value.
Wow, that is subtle.
Incredibly subtle. The paper uses a great analogy to try and convey this. Detecting this tiny deficit is like, imagine a whole bucket of sand that's overwhelmingly yellow, but you expect maybe one small scoop's worth of brown sand mixed in.
Okay, that's the standard Earth K40 level, of the tiny bit of brown.
Right. What they found in these samples was like finding only a single grain of brown sand in that whole bucket instead of the scoopful, an even tinier deficit within an already trace amount.
That really puts the required precision into perspective. It's amazing they could measure that reliably.
It's a testament to the advancements in mass spectrometry and clean lab techniques. But the consistency across these geographically distinct samples, representing both ancient crust and deep mantle, pointed to something real.
The conclusion being, these materials were built different.
Built different, chemically speaking. They carry a different potassium isotope signature, specifically this K40 deficit, compared to the vast majority of accessible Earth materials. They hadn't been fully processed or homogenized like the rest.
Okay, hold on. Finding a difference is one thing. Proving it's primordial, that it's actually from proto-Earth and not caused by something else later, that seems like a huge leap.
It is the absolute crucial next step. You find an anomaly, you have to ask, could anything else explain this? Could some geological process create this K40 deficit over billions of years?
Right, like maybe some weird chemical reaction deep in the mantle preferentially removes K40, or maybe interaction with seawater altered the Greenland rocks. You have to rule out secondary processes.
Exactly, and the researchers knew this. This moves us into the validation phase, which is arguably the most rigorous part of the study. They had to try and break their own hypothesis.
How did they do that? Through simulations?
Yes, through sophisticated numerical modeling. They started with the assumption. Let's assume these samples are leftover proto-Earth material, and that proto-Earth was originally deficient in K40.
Okay, start with that premise.
Then they simulated everything major that happened after that, all the potential alteration processes. They threw the geological kitchen sink at this hypothetical K40 deficient material in their models.
What kind of processes did they simulate?
Two main categories. First, the big one. The giant impact itself and subsequent smaller but still significant meteorite impacts throughout Earth's history. They used the known compositions of different meteorite types to see if mixing that stuff in could dilute or change the signature.
Could the impact have somehow created the deficit?
Or could mixing with impactor material explain it? That was one set of tests. The second category was simulating long-term geological processing within the Earth.
Like the mantle convection, heating, melting we talked about.
Precisely. They modeled the effects of high pressures and temperatures deep in the mantle, processes like partial melting, where only some minerals melt, fluid circulation, basically anything that could chemically alter rocks over billions of years. Could those processes generate a K40 deficit?
Okay, so they simulated impacts and internal geology acting on this hypothetical K40 pore starting material. What did the simulations show?
The results were incredibly clear and strongly supportive of the primordial origin.
How so?
In every simulation they ran where the original K40 deficient material was subjected to either impact mixing or long-term geological heating and processing. The end result was a composition with a higher proportion of K40.
Higher, not lower.
Higher, or at least it evolved towards the standard modern Earth K40 ratio. The processing, the mixing, the heating, it always tended to increase the relative amount of K40, bringing it in line with the homogenized bulk Earth value we see almost everywhere else.
And crucially, none of the simulations could reproduce the persistent K40 deficit that they actually measured in the Greenland, Canada, and Hawaii samples. No known impact scenario, no known geological process acting over time could explain why these specific rocks have less K40 than everything else. Wow. Okay, so if later processes only make the K40 level go up towards the standard value,
then the only logical explanation left is that the deficit is intrinsic to the material. It started out that way and has somehow remained largely unchanged.
it's a primary feature, not something created later.
Exactly. The inescapable conclusion is that the K40 deficit must be a relic, a chemical memory of the material's formation conditions before the giant impact, before the great homogenization event.
So these rocks, the ancient cratons, the deep mantle source tapped by Hawaii, they really are leftover pieces of proto-Earth, preserved somehow.
Preserved, perhaps sequestered deep in the mantle, maybe stabilized in the ancient crust, escaping the main mixing bowl for 4.5 billion years. This tiny isotopic deficit is like a surviving echo from a lost world.
That is quite stunning. It opens a window we thought was welded shut. But the story doesn't quite end there, does it? There is another twist, a contradiction almost.
Yes, and this is, in many ways, just as profound and maybe even more mysterious. It leads to some big unanswered questions.
While these samples confirm that some kind of proto-Earth material survived, the specific chemical fingerprint they found that exact K40 deficit combined with the K39-K41 ratio.
It doesn't perfectly match any known type of meteorite in our collections.
Wait, really? After the whole setup was about using meteorite anomalies as a guide.
Isn't that fascinating? Remember, the 2023 study showed different meteorite groups had different potassium anomalies. That gave them the idea to look for an anomaly on Earth. They found one, the K40 deficit.
Yeah.
But when they compared the specific isotopic ratio of this proto-Earth material to all the known meteorite groups,
No match. Not carbonaceous chondrites, not enstatite chondrites, nothing.
no precise match. It's unique. It's clearly ancient, clearly distinct from bulk Earth, but it doesn't align perfectly with any of the standard meteorite proxies we use for early solar system ingredients.
What does that mean? It feels like a major curveball.
It's huge. It implies that the specific type of material, the particular chemical building block that came together to form the bulk of proto-Earth, we haven't actually found a sample of it yet in our meteorite collections.
So the stuff that made us predominantly is missing from our samples of the early solar system.
That seems to be the implication. Meteorites help point the way by showing anomalies exist, but the specific flavor of anomaly that characterizes proto-Earth appears to be from a type of material we haven't yet identified or sampled out there.
That throws a massive wrench into models of planet formation, doesn't it? Scientists have spent ages trying to figure out Earth's composition by mixing different known meteorite types in various proportions.
Right. They try to create recipes, 80% this chondrite, 15% that one, 5% of another to match Earth's overall chemistry. But if the main ingredient, the proto-Earth stuff itself, isn't represented in those known meteorite groups,
then those recipes are fundamentally incomplete. They're missing the primary component.
it suggests our sampling of the early solar system, based on the meteorites that happened to fall to Earth, might be biased or incomplete. There could have been distinct chemical reservoirs back then that we just don't have good samples of.
Which makes sense. Maybe the stuff that preferentially formed Earth in this region of the solar system wasn't the same stuff that ended up forming asteroids further out, which are the source of most meteorites.
That's a strong possibility. Maybe there were compositional gradients in the early solar nebula? This finding really highlights that gap in our knowledge. It's what Nicole Nee alluded to in her final quote they shared. Our study shows that the current meteorite inventory is not complete, and there is much more to learn about where our planet came from.
We found the ghost of proto-Earth, but we haven't found the ghost of its specific parent material in space.
Well put. The material that built our world seems chemically distinct from the common samples we get from space. It raises huge questions. Why did this type of material accumulate here? Where does it come from? And is any of it still out there?
Okay, let's try and bring this all together as we wrap up. This has been a pretty mind-bending journey into deep time and deep Earth.
It really has.
We started with the idea that proto-Earth's chemical memory was erased. But this new research, using incredibly precise measurements of potassium isotopes in very specific rock samples.
Samples from ancient Greenland and Canada and deep mantle lavas from Hawaii.
They found a consistent deficit in potassium-40, a tiny chemical flaw.
A flaw that couldn't be explained by the giant impact or subsequent geological mixing, according to their simulations.
Proving that it must be a primordial signature, a leftover piece of the original pre-impact planet that somehow survived the cataclysm and billions of years of churning.
It's direct chemical evidence that parts of proto-Earth are still here, hidden within the modern planet.
And this isn't just, a cool historical factoid for geochemists. As you listen to this, understand that this fundamentally rewrites the opening chapter of our planet's story.
It absolutely does. It tells us the giant impact wasn't a perfect reset button. And it suggests the building blocks available in the early solar system were more diverse than we knew based on meteorites alone.
It also implies that our planet's interior, particularly the deep mantle, might not be the well-mixed soup we often imagine. There could be these ancient, chemically distinct blobs or reservoirs down there.
Holding on to secrets from the dawn of the solar system right beneath our feet, which dramatically shifts the focus of future research.
How so?
Well, for decades, the primary way to study Earth's origins was looking outward, analyzing meteorites, modeling accretion from known space materials. Now
the search turns inward.
Exactly. We need to explore the deep Earth with new tools, new perspectives. We need to look for other isotopic tracers, other chemical anomalies that might be preserved in these deep, isolated mantle reservoirs, potentially sampled by plumes like Hawaii's. The mantle becomes a geological archive.
Okay, and here's the final thought, the real provocation perhaps to leave you with. We found evidence for proto-Earth material identified by its unique potassium signature.
Yes.
But that signature doesn't match any meteorite we've ever found, the specific stuff that came together to build this world, our home.
Its precise starting ingredient remains a mystery in terms of samples we hold.
Which means that the most fundamental component that created us is either still out there somewhere in the solar system, maybe locked up in asteroids or planets we haven't sampled properly, waiting to be found. Or maybe it was mostly used up or destroyed in the chaos of planet formation.
It's a profound unknown. We're standing on the evidence of our origins, yet the perfect match for that starting material is elusive. It forces us to wonder if this potassium signature survived, what other ancient chemical secrets might be locked away deep inside Earth, just waiting for us to find the right isotopic key to unlock them. What else don't we know about the very foundations of our own planet?